Today we will start tending towards some interesting things, but first we must have a bit of background still. Just some words about one form to also remind you of the situation. So the space of one forms is denoted on a manifold M is denoted by E1 of M. And I usually write a form as with Greek letters, so omega. And what this is, of course, is it is a mapping, so it's a dual object to vector fields. And it applies to a vector field, and you get a C infinity function. This is now the notation we will use for C infinity functions. And it has two properties. Of course, it's linear. In the sense over the constants, it's linear, it's over constant. Oh, it's additive, excuse me. Of course. But it's more than just linear over the constants. It's linear over the C infinity functions. So it is dual in the sense of the module structure on the C infinity function. So that's what one's forms are. We have a nice remark that there's a God-given operator, D, who functions to one forms. As I say, I tried to make propaganda for one forms. They somehow are better. And here's an example. You have this God-given function. Namely, it takes a function and applies it to a vector field by applying the vector field to the functions. It's sort of silly, but very important. Now, we discussed this, but I really like to re-emphasize this, is that D of a product, let's do the calculation here. It's, you apply X to the product, but X is a derivation, so that's F, G, X applied to G, plus G, X applied to F. And if you do this out, what does that mean? This is here F dg of X plus G dF of X. So we prove that this operator satisfies this sort of Leibniz rule, D of F, product rule or Leibniz rule. So to do this right, this would be F here dg plus D G dF. So in some sense that is the first step, that is it. What I would like to emphasize some basic properties. Some basic property that I mentioned the last time. Several basic properties. One is that it makes sense to restrict one form to open sets. So it's the usual picture that I'm drawing. You have a manifold, and this is a global thing, but you may want to restrict to an open set. An open set in the manifold, and restriction makes sense. So you can restrict to this open set. Omega can be restricted to the open set and in the way we expect and want. So I talked about that last time. But if you have a point here, for example, in a coordinate chart, you might want to really even talk about omega at that point. Now, please think by analogy here with tangent fields. So if we have a vector field on X, on M, then I can restrict the vector field to an open set, and then I can restrict it further. I talked about global localization, even the nano level, really at a point. Here I can do the same. So, to be very precise, this thing is a vector field on the open set. And of course, what you get here, you get omega is a one form on the open set, so the restriction from a global one form is just a one form on the open set. And here, when you restrict, this thing is a tangent vector, so this thing, let's write it, is in the tangent space at that point. Okay? Yeah. What?
CPM,
Yeah, I'm sorry. Yeah. And this is a simple matter, and you can really just check it also for one forms, is that okay, if X is a vector field on an open set, let's say, and this thing is a coordinate chart, then you've got coordinates, let's say X, that means that X is some AI ddxi, I've said this 100 times, where these things are functions. And then if you really localize it at the tangent space level, this is X at the tangent space is the same thing, AI, but at the point, so now it's a number times the derivative at that point. So the global setting to the coordinate chart setting to the point setting. This makes sense, and we checked it. Okay. You can also check it. I think now I'll explain how there's some hints in the homework and have you check that for one form. It makes sense to, it is well defined what it means to evaluate a one form at a point. In coordinates, if omega is some AI dxi, then omega at a point is just what you think it is. Omega at a point is what you think it is. It's just you evaluate the coefficients at that point. And I quite often write dxi at that point. And dxi of the point is what you think it is. Dxi is the dual basis. So this is the dual frame. To the basis of fields, to the basis of tangent vectors. So all of that makes sense. And since it makes sense, we were able to define so let's do it this way. We're able to define the pullback process as follows. If you have a map from a manifold, let's say, let's be precise about this, an m-dimensional manifold into an n-dimensional manifold, and you have a form on the n-dimensional manifold, then you pull it back to get a form on the n-dimensional, the original manifold. Okay, so you should think we have a certain mapping with obvious properties, the pullback mapping from forms on the target manifold to the domain. Again, vector fields don't work this way. This is another argument for forms instead of vector fields. Yeah.
Can I please ask, I don't see what kind of object is dxi of p? What kind of object is
dxi at p is defined as the dual basis to the basis ddxi at p. Just, I gave the definition here. So, but maybe let me formalize it.
It's a function? As an object, is it a function?
It's a linear function on the tangent space. So let me make this very precise, okay? So we have the tangent space at P of n has a frame, a basis, ordered basis, d dx1 at p through d dxn. That's no problem with that. And the cotangent space, I'm introducing, and I thank you for your question because it reminds me to introduce the notion of the cotangent space at M. This is the dual space, just as a vector space of the tangent space. And it has a frame. The frame is the dual basis to the above, the ordered dual basis. And this ordered dual basis, notation-wise, is dx1 at p through dx at p. Okay? That's what I meant by saying, here is the definition of ddxip, just the dual basis here. Okay? Thank you. Perhaps conclusion of the notation. So again, it's very important, global stuff, coordinate charts, right at a point. Tangent vectors, vector fields go down to tangent vectors, forms go down to cotangent vectors. Okay? So this, the elements of the dual space, this is called the cotangent space, and elements here are called cotangent vectors.
Do they have a geometrical representation?
Huh?
Do those vectors have a geometrical representation?
They are linear functions on the tangent space. I mean, that's okay. So I would even, so his question was, don't these things have a geometrical representation? Or do they? Right? And the answer to that question is if and only if the tangent space is equipped with a non-degenerate bilinear pairing. So that in fact, you can interpret a cotangent vector, a function, as a vector. The only way to interpret something in V star as a vector in V is by representing it as through a function, through a bilinear form. So the nice question, so a geometric representation of a cotangent vector, a function here, say at a point, is you have f is equal to a vector applied to something. Okay? Let me even emphasize a notation here. This means that this, I will put a notation here, P. This means that if we must have some bilinear pairing that is non-degenerate, get this, bilinear, non-degenerate, to make this possible, that every function is represented in this way. So there's a one-to-one correspondence, there's even a linear correspondence from functions to vectors, but if and only if you have this pairing. Now you always have such a pairing. There are millions of such pairings. There's a big continuum of such pairings. So everybody says do it. Take the pairing and do it. Okay? But if you're in a model, for example, of a physical situation, you better know what pairing you're dealing with. You understand? This pairing may give you the entire physics of the situation. It may give you the entire mathematics of the situation. Okay? So Mihai's question is, can you represent this as a vector? The answer is yes, if and only if you have a good pairing. So I answer his question with a tautology. He said he wants to see the geometry. And I say, in order to do that, I have to introduce geometry. This is geometry. Because you have norm, right? You have inner product, you have angle, you have projection, right? These things we talked about the other day. I emphasize later on, this will be a very fundamental thing. We will have such pairing, and the pairing will vary with the point. Every situation in modern mathematics or in physics, the pairings will definitely vary with the point. You may be lucky that you prove a theorem under a lot of assumptions that the pairing is constant somehow. But, or you may find coordinates so that it's constant, but they won't be natural. Okay. Thanks as usual for the question. Okay, so that's what this pullback is. This pullback, recall the pullback of, I'm going to write it here. Maybe if I think I have to write it here to get good light on it. The pullback of omega at a point P, what you do to get this is you apply omega at P, well, you have to say what it means to, no, let's do it this way. The pullback of omega applied to a vector field, I have to tell you what that is. I pull it back, I apply it. Well, I'll tell you what it is at P. What it is at P is I push over the function value. That's a function, omega and f of P, applied to the push forward of this tangent vector. Okay, and that's the definition. And we talked about it in great detail last time. I'll give you some experience in the homework of computing these things in coordinates. But I wanted to emphasize, and now we're coming back to the discussion at the end of the last lecture, is if you have a curve, gamma, say from an interval 0, 1, into, say, R2 as an example, I just want to give you an example, then you define the integral over gamma of a 1 form, so you integrate, that's the reason for the number 1. Okay, I'll tell you something about the future. 2 forms you integrate over 2-dimensional things, 3 forms you integrate over 3-dimensional, whatever they are. Okay, 1 forms you integrate over curves. Okay, so we integrate a 1 form over a curve. That's the integral, you just pull it back to the curve and integrate it. Okay? And now the question is, if this curve, if the parameter here on this interval from 0 to, say, 1, if this parameter is t, say this is the t parameter here, then this will be the integral of some function, f of t, let me call it h to try to be consistent with the last lecture, h of t dt, and it's of interest, and I mean here the integral you learn in high school. That's what it means, the integral, the high school integral, h of t dt. This is a smooth function, okay? So it's easy, you know how to integrate a smooth function. This is nothing subtle. So h, it's a smooth function, so how do you integrate? You have to figure out what h is. And last time I drew this picture on the board. So this is a vector field, so that the tangent field is at x point ddx, of course at the point t. I won't write at the point. Now the teachers get tired of writing, so they don't tell you where they are, but I think you have enough experience to know where at the point gamma of t. And you will have a form here, omega, at this point. So omega equals, say, f dx plus g dy. And so you pull back this form of omega, and you get, let me write it now as a function of t dt. So it's a function of this one form variable. Well, I did it yesterday, so you know what the answer is f at gamma of t times x point at t plus g of gamma of t times y point of t. Now, as you see here, this is.
Does it make sense to put also dt there?
Pardon?
Does it make sense to put dt there and not on the other side?
dt. I'm sorry. So
Not dt, shouldn't be in the other side? Sure.
Is that what you mean? Yeah. Yeah. I pull back the form. This is a one form on the interval. We have coordinates on the interval. The coordinates are, maybe we should go through it. The coordinate on the interval is t. Right? Right? The frame for the tangent space is ddt. The dual basis is dt. Right? Now you know what dt is. Okay? It's a dual basis. But here the interpretation dt tells you that you've got to integrate this as the Riemann integral. Okay? Yeah?
Can I ask a question? Why do you put dt in the left side? Last time we
The
didn't.
pullback.
We didn't put it last
Oh, I shouldn't have. That's what you were saying,
Yeah.
right? That's what I'm terribly sorry. Now it makes sense, right? The left-hand side is already, dt is built into this thing.
Yeah,
That's what you were saying. Sure, of course you're right. So, I'm sorry, what I meant to say here is h of t dt. To be consistent with this. So you see, it looks like scalar product, and if you accept the scalar product as the right geometry for this situation, then you can dualize cotangent vectors to tangent vectors and regard the cotangent one form as a vector field. And so you, in that sense, if you believe that geometry, then you computed work in this situation by integrating over a curve. But there's no reason to believe that geometry. There's no geometry in the picture. Okay. That's it with one form. Now the next theme is a fundamental theme of mathematics after the Second World War. So everything I've talked about here you can translate into something that Newton might have understood. You know, if you just retranslate into coordinates, you have derivatives, okay, you have dx. Leibniz claimed he understood what dx is. These physics guys, you can call it delta x if you want. All these things you can retranslate into classical mathematics. This is a better viewpoint out from my point of view. But what I'm about to talk to you now is one of the fundamental, maybe one of the most fundamental concepts in modern physics, and one of the most fundamental concepts in mathematics, starting, roughly speaking, in the late 1940s and early 1950s. The fundamental book in this subject was written in 1952. So the subject is called Introduction to Fiber Bundles. This notion existed implicitly in physics using other words. You've heard notions like gauge transformations, gauge group, and all of these things. These are certain objects related to certain fiber bundles. But fortunately, mathematicians translated this in a way that we could understand. So the fundamental book, which I still find very good, I think Steenrod wrote this in 1952, maybe the same subject, Introduction to Fiber Bundles. I'm going to explain fiber bundles, but the main interest I'm going to explain main interesting bundles will be the tangent bundle and the cotangent bundle. These are fundamental examples of what we call vector bundles. Now, we're going to introduce this concept, first of all, in a completely formal way. Okay? You'll see that immediately. And then, very soon, we are going to have smooth structures on these objects so that we can do geometry. You can't, geometry, my kind of geometry requires at least piecewise smooth structures. I don't know what to do without piecewise. I accept the tetrahedron, I mean, you know, the corners. Or I accept cones and singularities of algebraic nature, basically. I need some smooth structure so I can do analysis in geometry and algebra at the same time. Okay. That's maybe not consistent with many people, but that's my point of view. Okay. So, you can tell your mother by email tonight. A fiber bundle, she might get excited when she hears this word fiber bundle. You're going to like this definition, your mother's going to love this, is a bundle of fibers. Well, okay. Now, okay, your mother knows better about this, at least my mother knew, because she was always giving, my mother was a math teacher, by the way, who loved to solve geometric math problems while taking a bath. Sometimes at age 9, I would hear my mother talking in the bathroom about, you know, some non-trivial thing in high school geometry. She's a great geometrist. But she made presents for people, you know, and she would take, but she wouldn't wrap them in all sorts of paper. She would put maybe some things like this and then put some wrapping around it and give, you know, like a flower, a bunch of flowers, for example. A nice ribbon around this thing. Well, these things are fibers, let's say from my mother, and she would have been 100 years old this year. And sometimes she wrote a ribbon around here, right? So it's a bundle of fibers with some idea of some smooth structure of going from fiber to fiber because there's this ribbon around it. You see what I mean? That's smoothly moving around from fiber to fiber. So first of all, it is a fiber bundle with some possibility of smooth movement around with a ribbon like this over a basis. Now my mother's fiber bundle were a highly non-trivial fiber bundle with little flowers and things like this. Now, you should learn, if you're I hope you all become professors, that when you explain something, you should explain something what it's more or less like this, but then you should also explain something what it's not like. To explain something to a child, it's much easier to say it's not like that. No, it's not like that. Keep saying what it's not like, and then the child, if he's inquisitive, will say, well, is it like this? You see? This is the best thing. And then you say, no, you idiot. No. No, of course not. So, okay, so I want to emphasize, it's not like my mother with the little things at the top like that. Every fiber is in some sense the same. Now, in some sense, this is really interesting. Because in some sense in mathematics means isomorphism. Right? It means you don't care about a lot of properties, but it's isomorphic. The two things are isomorphic. If you would look at them geometrically, I mean, you're asking for a geometry, and I don't object to that at all. If you would have a way of measuring geometry, you might see the one fiber looks smaller or bigger than another in some sense. But what I mean here is, for example, here is a circle, and here's a nearby circle, and here's a bigger circle, and a smaller circle. Okay? So in some sense, you see, if you have a little bundle of circles, this is called an S1 bundle. If you visualize it in a geometric way with your eyes, so that means you have a geometry, the S1s might be changing in size, in area, right? And by the way, when that happens, what could happen is there could be a catastrophe when they go to very small size. And that is not allowed in a bundle because all the fibers are isomorphic. That is, so to speak, a degeneration of fibers. We talk about degenerating the fibers to something which is not like the other fibers. Okay, downstairs will be my manifold N. Oh no, I'll use a general notation. Downstairs will be the letter B. And the letter B stands for base. Because it's the base of this vibration. It's the base, and you think of the vibration over this base. And I follow the notation of many people, in particular Steenrod in the old days. It's, by the way, one of the few books I've ever read, and I like very much. The upstairs space, so this is downstairs space is called base. And the upstairs space is called entire space. Okay. Bundle of fibers, they're all isomorphic to one fiber. So F is the abstract fiber. I want to tell you what I mean by that. Oh, I'm sorry. Here you have this S1 bundle. Here is a varying geometry, but these S1s every fiber is isomorphic to S1. That means I have a fixed abstract fiber, which is S1. You understand? Here is a point B in the base. I have an S1. These colors are not too good, I'm sorry. Let's see here. That color is a little bit better. Yeah, this is the color. So this fiber, this fiber here over this point B is isomorphic here to S1 by an isomorphism, whatever it means, isomorphism phi, which depends on the base point. Right. This little tiny fiber here, let's say this is B hat. B hat here, this is the fiber over B hat. Here's the fiber over B hat. This is isomorphic to S1 by another isomorphism because it's another fiber. Do you get it? So a fiber bundle, formally speaking, is a bundle of fibers. There's a map from this total space or entire space to the parameter space. Each fiber is isomorphic to a fixed fiber, which I call the abstract fiber. Okay, this is what I call F. The isomorphisms don't need to be chosen, but they're at least isomorphic. So, example.
So does the fiber bundle just have some generators?
What does that mean?
I mean, we can call them generators, like the base, the function, and the abstract
Yeah,
fiber.
we're going to, yeah, thank you very much. I'm going to write the formal notation now, okay? So let's write the notation E. It's the entire space. So it's, right now it's just a set. There's a mapping surjective onto base space. right now it's formal. Okay? The letter here I'm going to write E sub B to remind you it's over the base point B on the base, is the pre-image of B. So for every B, we have this pre-image. For BU, we have this pre-image. Is it clear? We have each pre-image.
So
Yeah?
E is the space of all fibers, or
That's right.
of all the points on the fiber?
Do you understand his question? The space of all fibers is B.
Okay.
The space of all points on the fiber
Okay, so it's like
is E.
pi is like a quotient map?
Pi
It's
is
like a
something
projection?
like a quotient map.
It's a projection.
It's somehow only, you have the space of all points on a given fiber, and you just suddenly regard it as a fiber. Or I said it the other way around. The point on the base is a parameter space for this fiber. Okay?
Professor, you write base as a line. Could I say that the fibers have some structure of continuity?
Yes, very good. We're going to talk, he's asking about structure now, and I've used the word isomorphism quite often, so I better have some structure in mind. Yeah? Okay? Okay? So, F is another space. This is the abstract fiber. Okay, and I said for each B, you better have an isomorphism Phoebe. That's a woman's name, Phoebe. I don't know in which language, but I know some women named Phoebe. Maybe it's French, I don't know. Phoebe, Phi sub D. From here to the abstract fiber should be an isomorphism.
Just isomorphic, isn't it? I mean,
Huh?
shouldn't it be homeomorphic?
Right now, bijective. This is somewhat your question. Okay? So that's what I say. My first introduction to this subject is upstairs space, downstairs space, fibers. It's purely formal. But each fiber is the same because each fiber is equipped with an isomorphism to a fixed thing. So in that sense, isomorphism in the sense of bijective. Okay? However, F will be equipped with structure in every example. Okay? And I will talk about that in the context of the tangent bundle now. Okay? So the example, so what I've discussed so far is very formal, but we're coming close to something realistic. The tangent bundle. This is not abstract nonsense. Let me just tell you what we are doing as a long-term goal. We are going to study here vector fields and one forms and all of this stuff. All of these spaces, the space of vector fields, the space of one forms, and all of this stuff, are infinite dimensional and horrible. The spaces themselves are really very difficult to handle. We are going to replace our considerations of these spaces with geometric objects. So instead of considering all the time this huge space of vector fields, we are going to consider something called a vector bundle, which is a geometric object associated to the manifold. Instead of considering the space of all these one forms with all these A, I, J, K, L, M, N, O, P, alpha, beta, gamma, and so on, we're going to understand the cotangent bundle. It's a canonically associated object to the manifold. It is of fundamental importance in physics. I guarantee you, every theoretical physicist for sure will guarantee it. The home of classical mechanics, the home, absolute home of classical mechanics is the cotangent bundle of a manifold. The lingo in physics is the manifold is called the configuration space, you've heard this word, and the cotangent bundle, the upstairs space, is called the phase space. Physics is formulated as a very, very bad differential equation on configuration space is where we're living. Physics is second order, you must agree. X double point equals 0, for example. Or, X double point equals G or minus, what is that? That's a second order differential equation, and you can imagine second order differential equations are very Laplacian and so on are difficult. Right? These differential equations are interpreted on the cotangent bundle as first order differential equations. They are vector fields on the cotangent bundle. This is the home of classical mechanics. I guarantee you, when you see in one lecture I produce all basic results in classical mechanics by just looking at the cotangent bundle, I'm sure you will be convinced. Okay? And this is also, I've talked to your professor in physics, Professor Schultz, he agrees completely with me on this point. And so you'll be very happy that I've introduced these things. We're replacing these very complicated spaces of vector fields, one forms, and so on, with certain bundles. Okay? So let's go very slowly. Here's the manifold. In this case, this is the base space. If you take a point P in the base space, you have the tangent space at P. If you take another point P hat in the base space, you have the tangent space at P hat. If you take any point in the base space, you have its tangent space. You have this feeling? No problem with feeling so far, okay? Just this feeling. To every point, you have its tangent space. Okay? Now, these fibers, so here, this is the tangent bundle. This is what I call the entire space in the other place. I told you that we need an isomorphism to, I'm getting to your question now, to a fixed fiber. Okay? Okay. So we need an isomorphism, phi p, of a tangent space to each fiber. I always call it X. To each fiber, to the fiber, and you see all of these tangent spaces are different.
They all look like Rn. They all look like Rn.
Very good. So this is so first of all, you're absolutely right. Let me just comment, however. If you have a manifold, look at a sphere. You see a sphere? You see all these tangent spaces around. I'm telling you, they are different. They're not the same space. It is a fundamental remark. These tangent spaces are all different. You have this tangent bundle, but they're all different. Right? So, what Mihai is suggesting is each one of them is isomorphic to Rn. Now, Rn is a vector space, and it has vector space structure, and it tells you that there are many isomorphisms you could have here, but they better be compatible. I mean, you agree there are many isomorphisms possible here to Rn. If I give you one isomorphism, and this is what I've tried to start at the beginning of this lecture, I give you one isomorphism, give another, what's the difference? How do you get from the one to the other? By matrix, GLN, right? Two isomorphisms, right? One phi1, phi2, Rn, this is really a matrix, or a GLN, right? Well, it says any two should differ by an element G in GLN R. I'm doing a real vector bundle here. Okay? Now, I'm trying to get to your question of structure. Okay? I have two bijective maps, say, but they differ only by GLN. That means really I'm considering this fiber as a vector space, right? Because no matter how I pull back the vector space structure on Rn with these bijective maps, it's well defined, right? So I'm really considering that thing as a vector space. If the fiber were a group, even a finite group, or anything you like, your favorite group, the change, I take isomorphism 1, isomorphism 2, I want this thing to be compatible with the group structure, that means it should be an automorphism of that group. Right? Group. What other object do you know? I don't know, they're fancy words. Fields. I don't care. Any structure you like. Topological space. If this is a bijective map to this topological space, you know what an open set means here. I want to transfer this information back here. This means that any other one that I'm going to use to identify here better be compatible. So the group is going to be the full group of homeomorphisms. If it's just a differentiable structure, it's going to be the full group of diffeomorphisms. Those are horrible groups. They're huge. Okay? But this thing here is called the structure group. So a vector bundle is an upstairs space with all these vector spaces. In what sense vector space? Each one comes with a bijective map to a fixed vector space, Mihai's vector space Rn. We pull back the structure there, it's vector space. Right? That's well defined because I only allow things that are in GLN. It doesn't change the notion of a vector space. Okay? Therefore it's called the structure group. Okay? So the final thing is the structure group G. Of course, I've had many students over my life, but, oh, excuse me, yeah.
So, you use a group G because, I mean, why don't you use like a notion of continuity?
I just told you, if I'm interested in a fiber bundle in the setting where there's no algebraic structure, for example, on the fiber of interest, but I want the fibers to all be topologically equal to something, the structure group will be the group of homeomorphisms of that fiber.
No, but in this case, in Rn we have continuity. Why does
If you're absolutely, okay, fine. So that's very good. So let's take an example, say we have Rn, everything's the same. Except now, what you're saying is I couldn't care less about that thing being a vector space. I do care that it's a topological space. So you say all of these identifications differ only by homeomorphism. That says if I pull back the topological structure by the original bijective map or by another bijective map, it doesn't matter. So I equip this fiber with the structure of Rn. And it's well defined. The point is, I don't want to tell you which bijective map I have. I mean, come on, there are all sorts of ones. But they only differ by what's going on in the fiber. Okay? Okay. Fibers, base, yeah? Fiber is isomorphic to a fixed thing, and these various isomorphisms you're allowed to choose only vary by something in the structure group. This is a fundamental concept in modern mathematics, I guarantee you. Okay. Guarantee you. Okay, so here it is, fiber bundle. And here, in this context here, is if F equals Rn, Or, let's just say, to make it clear, it could be Cn, or it could be any sort of a vector space you wish. So anything you wish in terms of vector space. And G is equal to GLN R or GLNC or something like this. It doesn't matter, whatever the linear group is. This thing is called E over B, so the total space over the base space is called a vector bundle. And the reason it's called a vector bundle is it's a bundle of vector spaces. Yeah, Alexander.
It's still not clear to me what you mean by the differ. You mean the bijections at two distinct points, they differ
No.
from each other?
Yeah, I should repeat what I meant, okay? I think we're going to come to your question in a half a second, but let me repeat what I said. I have a fixed fiber, and Alexandros, you give me a bijection, and you say that I want to use that bijection to define a vector space structure on my fiber, okay? And I say, but come on. Yeah, Rushdon gives me another bijection. I mean, I don't know you guys whether you have the same bijection or not, right? And all I require here is that you're well defined between you. Yeah, I don't require the same bijection. Who knows? I only require on one fiber now. I think you asked about varying fibers. I only require that you two only differ by GLNR transformation. Okay, that's what I mean.
So we consider all of these bijections.
Yes, every fiber comes with a bijection or with all possible bijections. That's the way you should think about it. Yeah? That's right. That's the way you should think of it. Any possible bijection. Okay.
So Professor, here the abstract fiber is not a member of the entire space.
I understand what you're saying. And in some sense, the answer, you see here the abstract, in the tangent bundle case. The fibers really are varying, they're different, and they're only all isomorphic to Rn. But there might be a time when you really even see that the abstract fiber is the same as for every space. Okay? In other words, you have a choice somehow of an isomorphic. So I can go either way on answering your question. Okay?
So like here the abstract fiber is not unique.
It's some abstract other place. You have your vector bundle over here, and I have the fiber here, and I know all the fibers are here, and I say, okay, I know what the vector space structure is you're taking over there. Here it is. But okay. You might be able to take it over once and fix it for one fiber, right? Then all the other fibers are different, right? You have a sphere, and you say, okay, look at the North Pole. That's completely obviously R2, because I can push it down to the plane, and it's R2, right? So I'm going to fix that as R2, but all the other functions are different, and I need isomorphism. This discussion we're having here now, we ought to sell it, because we are discussing, I mean really, put it on YouTube and sell it, because we're discussing the fundamental things going on here. All of these questions are terrific, okay? You're really asking deep questions, for example, about Riemannian geometry, about the notion of connection, about all sorts of notions that really are involved in deep mathematics, appear immediately, right? These natural questions you're asking are appearing immediately. Okay? So this is a vector bundle. Okay. Now, this is still formal because I told you I really want this thing to be a manifold. I mean, there's nothing going on here. I only have the fibers, right? So you should get used to saying, well, the professor there, he handled somehow the vertical direction. Right? I told you that each one is a vector space or something like this, right? But he said nothing about the horizontal direction. So I need to tell you how these fibers are moving. Yeah, how somehow, what does it mean how they're moving? Somehow, I need to tell you the manifold structure here. Yeah?
Do you think a vector field? And that is a continuous function on the bundle?
Yeah. Very good. So, again, we're talking about basic concepts, and then Mihai asked a question that's very fundamental. So I don't object to answering that question at all. What Mihai has in mind, I think, just your intuition, what I see you feeling, is, well, I'm going to draw a new picture here so to clean it up. So here, let's say, here is a basic fiber, and here over this point, and he is feeling, he wants to understand the smooth, I'm guessing what you're feeling, is he wants to understand the smooth structure by taking a vector field on the base, and lifting it, if possible. So I'll just get an arrow here because it's so small, the dimension. So take a vector field on the base and lifting it here, here's the vector field lifted. I'm having a hard trouble drawing the arrows, but you see what I mean. I have the vectors here and I lift it upstairs, and then I push the fibers to nearby fibers by integrating the vector field. Right? That's what you had in mind, I think. Yeah? That's what you have in mind. That's a fundamental construction, but and I will love to use this all of the time, but in order to do it, I need a differentiable structure upstairs. I mean, I need to know what a vector field is upstairs, right? Otherwise, I don't know how to do it. Okay? So it's sort of putting the cart in front of the horse. Okay? But it's a good idea. So let me now come to the smooth structure. And for this notion of smooth structure, I need a few other words. You're going to really like the homework problems because using vector bundles, you're going to solve beautiful problems. And I need two simple notions. And I think one of the notions is related to what Alexandros was asking. So the first thing is restriction. Of E to an open set, U contained in the base. Now this is really stupid, but it could, at this level it could be any set, but it means here's the base, and here is this open set, and here is E, and here is a projection. It means just look at the projection over the open set, that's it. So you restrict your attention to all the fibers over this open set, just here. So restriction of E to the open set is just simply the pre-image of the open set. This mapping is up. Okay, maybe that's really boring. So for example, when I began studying mathematics, it was at the time when mathematicians in their lectures started everything with formalities. We first consider a set, A big letters A, B, C, D will denote set. Concept of an element, all these things are perhaps not defined in the usual logic of the time. An element of the set is denoted by small a in big A. The symbol A intersect B denotes the set of elements which are in A and B. The set A union B intersects, and then we have these operations of intersection and union. A intersect B union C equal. These highs, these are, I speak German. I'm starting, it gets formal, I speak German. These are called De Morgan's laws, I think. I hated it. I stopped going to class. I hated it. I hate, mathematics must be formalized and formulated beautifully and correctly, but that is the end product, not some notational, pushing notation around, right? This is not mathematics. So, this is more or less just notation. Pre and come on, give me a break. It's all the fibers over you, and that's what it is. All right. What you have to be careful about is the notion of bundle isomorphism.
Professor?
Yeah.
Is pi, the projection map, is it in the case of tangent bundle, is it bijective? Because you only requested surjective in the definition.
It's definitely not bijective.
It's not?
That's the same old question that you asked, I think.
So you can have two tangent spaces?
Well, I'm not sure what the question is you're asking. Over the point P, you have the tangent space at P. There are many, many tangent vectors in that space. The whole vector space is there.
Oh, yeah, no.
You're thinking of something else, I
Okay,
think.
yeah.
That's okay. Okay, but bundle isomorphism is a fundamental diagram. It is this. You have a bundle E1, projection 1, to the same base. So, E2 over B2. Now, you only discuss that matter when the fiber F is fixed and the structure group is fixed. Otherwise, you don't really have a bundle, right? You don't know what's going on here. Okay. Now, I think this is coming to what Alexandros is saying. Okay? A bundle isomorphism, let me call it a big phi, sits over the identity here. Okay? But it sits over the identity. You understand, if something sits over the identity, only stuff is going on in the fibers. Okay, that means that these mappings exist from fiber to fiber, but over the same point. Okay? If the fibers are vector spaces, what would you hope for this mapping? You would hope it would be linear.
GLM.
Yeah. No. No. They are not, be careful, that's a very good point. I can interpret it correctly, which is, he said they should be in GLNR. The fiber is not RN. But the fiber has a notion of linearity on it because it is identified with Rn by some mapping. The only thing you say is the linear isomorphism.
Yeah, but I mean, it changes structure very much. For example, it can be the zero matrix between them, and if anything is sent to zero, then we have linearity, but it doesn't say anything.
Okay, first of all, you're looking at something more general, a bundle endomorphism. I'm looking at an isomorphism here, so I want isomorphism between any two fibers. You said GL between the fiber in E1 over X and the fiber in...
Also, if it isomorphism is a GLM.
Yeah, but it's not GLN, it's a linear map. It's an isomorphism it's an isomorphism. Let me just emphasize this thing. This thing is fundamental to, this is an isomorphism from this vector space, it has vector space structure, to this vector space. You want to check if it's linear. You take some identification with Rn for the one, you take some identification from Rn to the other, and you check if it's in GLN or not. So you're right if you use one of those frames, or basic, okay? Okay. Now, what about triviality? So you can I told you to tell your mother about my mother and the fibers and this esoteric, and then you can tell your mother about all this fancy stuff. Bundle over a base, structure, group, fiber, blah, 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 automorphisms. And at the end of the lecture, you can tell your mother you're talking about a triviality. Okay? So triviality over U. It means, and now we go, the bundle over U is trivial. The trivial bundle, as you would guess, is just a product. Nothing changes. Okay? I've been intimidating him enough now that he probably wouldn't say this now, but he would say, at least over U, it's U cross Rn. Yeah? Yeah? He's right in the following sense. E over U is equal to U cross Rn by a bundle isomorphism phi by a bundle isomorphism phi.
We put identity below? We put identity below?
No.
No?
Oh, I'm sorry. Yeah, I thought you said phi. Where? So this, okay, it transports this. It transports the trivial product to the bundle space locally. Okay. Fine. If this is a coordinate chart, then
Isn't it isomorphic to R to N?
locally.
Yeah,
Yeah.
locally.
So if this is a coordinate chart, so he's thinking of the picture, he's got this thing, so this is then in Rn itself, just a piece of Rn, so some open piece in Rn. Then this thing here, what he just said is you should think of this thing as an open piece in R2n. But if you like, you could even think about it geometrically. Here is the first U alpha, but the second thing is very big. Right? The coordinate chart's not just some little ball. It's just the first variable is in some coordinate chart, but the other thing is that. Okay, it's clear. It's a local trivialization. That's a product. That's really trivial. Right? So you can tell your mother I talked about trivial stuff, and now I'm going to use these as coordinate charts, and now guess what I'm going to require? Change of coordinates smooth. Change of coordinates should be smooth. Come on, that's a manifold. Change of coordinates should be smooth. Okay? Now, this is really, really interesting. We have to have melodrama. Here's U alpha, and here are all these fibers over U alpha, okay? And over here is U beta. Actually, they overlap, right? Now, change of variables in the base is the usual change of variables in the manifold, right? So that's already smooth, because that's a coordinate chart. So that's the change of the coordinates from x alpha to x beta. Nobody needs to discuss that. In the fibers, what's going on here? It's a change of coordinates in the fibers. Okay, that means I have a fiber here over a point X, and I have a fiber here which is really over the same point, but in the coordinate chart I've got it in some other place, and we have to have a change of coordinates here. Well, it has to be linear. Otherwise, this whole thing is killed. The whole discussion is nonsense, right? Because I have local coordinates must respect the structure. So that means that the change of coordinates from this point here in this fiber to this point here, now you can say what you want, because this is Rn, and this is Rn, and this is GLN. Yeah? That's the smooth structure. That defines the smooth structure on the bundle.
Professor, are we talking about tangent bundle or?
Any vector bundle. Any vector bundle. Any fiber bundle. Well, I'm sorry. I discussed, I'm sorry. Here, the fiber is, I'm terribly sorry, the same, any fiber bundle, any vector bundle. Okay? Very good. I will emphasize this very strongly in the next lecture and in the homework. Remember, we will have something here. So change your variables of fiber variables, say. Fiber coordinates. You're used to this. I will call it G alpha beta from one coordinate to another. I will emphasize, however, that it depends on the base point. I'll say P in GLNR. Right? Because as I change the base point, this identification is going to be changed. Right? And since this has to be smooth, this is a mapping that should be smooth. So these so-called transition matrices are matrices which have smooth entries in them. It is a smooth map from the intersection into GLN. Okay? So you need a family of matrices with varying smoothly. Fortunately, GLN is a manifold. So I can tell you what a smooth map means. Okay? It has to be, change of the fiber coordinate has to be a smooth map from the overlap into GLN. And that is the smooth structure on a vector bundle. Now, if there was some other fiber bundle you asked, some other fiber, or some other structure group, you better understand what it means to smooth map into that structure group. Okay.
So do you mean that the abstract bundle could always be isomorphic to Rn?
As a fiber bundle?
Yeah.
As a vector bundle. So let's restrict to vector bundle.
Okay.
The abstract, in the case of vector bundles, it will always be Rn or Cn or something like this. You must choose something. That's what you asked about before. Choose, some fixed vector space. And we choose Rn, Cn, and so on. Okay? At least I do.
Yeah. So for example, if we change the F, but as a manifold, it still has a local structure of Rn, but then our abstract fiber will not be Rn anymore. Then would
It'd be something else. It could be a disk. It could be a circle. There's a big difference between the vector space R2 and a circle.
Okay.
So a circle bundle is a bundle of circles. Right? A circle, as you know, is a group. It's the rotation group. You might want to have the structure group be the group of rotations on the circle. So you might really want to preserve the notion of rotation. Yeah, that might be interesting. But certainly geometrically, totally different looking space. Right? Great, thank you very much. I really love this subject, as you see, and I think it's really, really fundamental.